beautiful session is Dr. Sharad Kumar Purohit sir. Sir is currently a professor at the Civil Engineering Department, School of Engineering, Institute of Technology and Nirma University. Sir has completed his Bachelor in Civil Engineering from BVM Engineering College, Vallabh Vidyanagar. Sir has earned MTech and PhD degrees with specialization in structural engineering from IIT Bombay. Sir has published about 70 research articles with international journals and international and national conferences. Dr. Purohit sir has been awarded with A.P. Nicolaides Prize, the Institution of Engineers, India, for the paper publications. Sir is also awarded first prize of National Award for Best MTech Thesis in Civil Engineering by Indian Society for Technical Education. It gives me immense pleasure to invite our next speaker, Dr. Sharad Kumar Purohit sir. Sir will take this session based on earthquake performance of masonry structures and retrofit strategies. Now, I would like to request Dr. Purohit sir to share his great experience and words of wisdom with us. Over to you, sir.
Thank you, Miss Amira, for your kind words. I hope I am audible.
Yeah, yes, sir. You are audible.
And let me check once again whether the screen is also visible or not. Is the screen visible?
Yes, sir. It's visible.
Okay. Thank you once again for making it convenient to be here. And first of all, I would like to thank Professor Sangvi and the other office bearers for this FDB for giving me an opportunity to share some of the experiences which has been gained over some period of time now. And thank you for conducting the faculty development program, which is a backbone of any academic growth in our country. And I'm sure the participant must have been enjoying various sessions of this FDP. And of course, I have gone through the schedule of the FDP, and I really once again congratulate the office bearers of this FDP, especially Professor Sangvi, for choosing the right kind of the subject and choosing the right kind of the titles for this FDP. Perhaps that once we integrate all this faculty development program topics, perhaps we can get some overall view about what is the current status of the earthquake engineering in our country, or maybe this part of the country. So once again, thank you very much for giving me an opportunity, and perhaps I would like to take over the next 1.5 hour maybe, in order to discuss some of the things related with the masonry structures. The masonry structure is considered to be one of the very common used typology in our country and maybe the most of the world. But there are certain issues related with the masonry structures when typically we try to look at in the view of an earthquake as an external force. So when in event of any earthquake, typically there are various type of the structures undergoing the damages, and we found out that masonry structures, because of their certain attributes, they might be behaving little differently, or they may be more vulnerable as compared to the other typologies that we have been practicing. So once again, I would like to thank the Professor Sangvi and team for allowing me to discuss this topic to the participant. Perhaps that can give us some thought-provoking ideas and some thought-provoking towards these masonry structures. So typically, I will try to put a little bit background on the masonry structures. And try to recollect all our understandings about the masonry structures in the first 20-25 minutes of the presentation. And definitely we would like to learn so many things, and from the experiences that what we had. So during past earthquake the scenarios, how our masonry structure has performed, and based on that our learning, experiential learning, that will lead us to that what different type of the damages that masonry structure is likely to undergo. And then obviously, as an output, as an engineer, we need to evaluate such kind of the damages, and how we can understand the extent of the damages both qualitatively and quantitatively. Once we start observing such kind of the structures and their performance in the past earthquake, and that's how we try to build upon such piece of information through various seismic evaluations. And while we are doing this, perhaps we come across that there are a lot of things required in order to carry out this seismic evaluation. And then obviously, as an outcome of such kind of the evaluations is definitely in the framework and in terms of the certain provisions for the masonry structures. So we are fortunate that as a country we have a certain codes available which do address some of the issues, which do guide us how to protect our masonry structures from the hazard or from the seismic hazard in the future as well. And obviously, when we move forward, perhaps we have to somewhere touch upon the structural masonry in terms of the properties and testing. So that I will try to cover with one of the studies conducted at our own university and in my civil engineering department. And obviously, as an outcome or as an outcome of our understanding, eventually as an engineer, we are supposed to provide the solutions, and that solution is in terms of rehabilitating or giving us some strength or reviving the strength of the masonry structures by offering some kind of a retrofitting strategy or retrofit strategies. And what are their current practices followed in our own country and maybe the globally, or maybe the various part of the world, that perhaps we'd like to touch up. And obviously, every engineering problems has certain challenges, and we have a way forward. So that is how I would like to, maybe toward the end of the end of the discussion, perhaps we will try to look at that as well. So, but before we start anything technical, let's have a quick updates on the last decade. What we have got in terms of an earthquake. So, in last decade, if you look at worldwide, we have a very big earthquake of magnitude greater than 7 and reaching almost up to 9 that has been happening on very regular time. So if you look at the first half of this last decade was very active from the seismic point of view, where almost every year we had a one or the another earthquake, but some of them are very well known and very much struck into our mind was Nepal earthquake of 2015, maybe because of the neighboring country with us, and we were sharing a lot of similar cultural values with them, and we have a similar topography of the building the construction. Perhaps that may be the one of the reason, but that was of a very concerned earthquake that we had in 2015. And the another one was Iran Iraq earthquake of 7.3. Of course, maybe the less causality, but there will be a lot of learnings that has happened. And there are other earthquake also of significance. But if we look at every day, there are a lot many earthquake event has been happening. And if we talk about yesterday, there was about total 36 earthquake in past day, and they may be of magnitude ranging between 2.5 and highest being 6.2. And the corresponding sources are already mentioned. But look at the Indian scenario. Some of the notable earthquake what we have faced as a country, where some of them listed with a very high magnitude, more than 8, maybe up to maximum of 8.7, ranging between 8.3 to 8.7 has been listed here, which are considered to be a major earthquake or a big earthquake, which include the Kutch earthquake, Assam earthquake, Kangra earthquake, Bihar Nepal earthquake, and Assam, sorry for the missing as Assam earthquake. And some of the earthquake of significance as far as India is concerned that are listed here. But if we are very well known, in fact, our generation is very well known that the real earthquake engineering has been started after this 1993 and 1997, back to back two major earthquake that has happened in our country. Of course, our generation civil engineers have learned a lot and perhaps got the motivation to work in the domain of earthquake engineering, maybe because of this 93 and 97 earthquake. By the time we were just having enough motivation, there was a big jolt in terms of 2001 Bhuj earthquake, which has really awakened the then generation of civil engineering, and it becomes now now there is a need of a national level motivation and national level requirement of understanding on the earthquake engineering. And you all very well aware, and perhaps some of my fellow colleagues have already talked about it, but I see consider that NPEEE, the formation of national program in earthquake engineering education, pioneerly done by Professor S.K. Jain and Professor C.V.R. Murthy, has completely changed the perspective of our generation civil engineering, and perhaps motivated many of us. One of is me in that, to work towards this earthquake engineering, and started taking a keen interest in learning the various aspect of engineering aspect of earthquake engineering. And then followed by that, we have a lot of other notable or earthquake of significance that has happened in our own country, and we have been seeing that what kind of the devastation, what kind of the loss that we have faced during such kind of an earthquake. And coming back to the domain where I need to talk about is about masonry. And we know the masonry is one of the earlier artifacts which has been very widely used almost all across the globe. And obviously that has been found, the
Pure sir,
civilization has been founded in terms
Pure
of.
sir, Pure sir.
Hello.
Yeah, so sorry to interrupt you.
Yeah, yeah.
Sir, तुम्हारी slide change नहीं थी.
Acha, okay,
हाँ,
is it
हाँ,
is
हाँ.
it like that?
Yes. It is only first slide and it is not in the presentation mode.
Uh-huh. Let
Yes,
me
sir.
check once again and do it. uh, is it changing in this mode?
Yes, it is changing right now. Yeah.
Okay, so let me stop sharing and reshare it. Perhaps that might help.
Yes.
That
That will
might
solve the
help.
problem. Yeah.
Yeah. I think that might help.
Yes.
Uh, I think you are able to see the some of my desktop folders.
Yes.
Is it
Yes.
is it
Yes.
true?
Yes.
Yeah.
Yes. Yes.
Let
Yes.
me open from here. Is it opening now?
Not yet.
Okay. Is it visible now?
No, only desktop folder. Yes.
So I'm just putting it in a presentation mode.
Yeah.
Now is it coming?
It is visible. Just for a moment.
It might take a time, maybe because
Yeah.
of heavy file. Is it yet not gone to a full slide mode?
No, no, not full slide mode. It is the folder and presentation both are visible right now.
Just a minute, sir. Let me go.
Excuse me,
Participating.
sir.
Participants.
Excuse me, sir. Sir,
Yeah,
Yes.
just put here this file on the desktop and then try to open it, sir.
okay, okay. I'll do that. I'll just give me a couple of minutes. I'll do that. I'll just take it on a desktop and then I open. That's what you suggest, no?
Yes, yes, sir.
And Purisa, if you share the screen, then I think this solve the problem.
Yeah, let me stop sharing first. Let me take that file on the desktop. Just a minute, sir. I should open it at desktop and then share.
Sir, the screen is not visible.
Yeah, correct. But should I now I have taken the file on the desktop. Should I
Okay.
open first the PPT and then I should share the desk?
Yes, yes, sir. First open the PPT
Okay.
and
Fine. So
then
let me,
share the screen.
okay,
There
fine.
is an option desktop oblique window.
Fine. So I have just opened the document at the desktop. Now I'm sharing it. I desktop and window,
Yes, sir.
and I have a three
Share
tabs to
screen first
choose
option.
upon. One is entire screen, second one is
Yes.
window, and third one is a Chrome tab. I used to get it go to
First
window, then
option
I will be
entire
able to see.
screen.
Correct? I should go to window, no?
Yes, entire screen. Entire screen,
Oh,
sir.
entire screen. I should go to entire screen. Fine. Now is it visible?
Yes, sir. It is visible now.
Now let me put it on a full screen mode. Is it visible now?
Uh, First, click on the PPT which you have opened.
Is it not going on a full screen mode now?
No, sir. At present, only the screen is visible, but the PPT is not visible.
Yeah, but not in a full screen mode, no?
Yes, it is in full screen mode.
So let me do it this way. Is it opening up now?
No, sir.
I'm able to see it in a full screen, but I think it is not at your.
Sir, escape from the full screen and then
Yeah, I have
open
escaped.
the open PPT.
Fine. So I have escaped it. So now I'm in a smaller version of the PPT.
But the PPT is not visible, sir.
Acha, PPT itself is not visible. Okay, let me once again try. Share. Uh, should I try with this Windows?
Yes, you can try, sir.
Yeah. Is it visible now?
Yes, it is visible now. Now make it in presentation mode, sir.
Let me try and put it in a slideshow. Is it coming up in a slideshow mode?
No. present.
I'm able to see it in a full slide mode, but not you. Is it changing the slide?
No, the slide is not changing.
Okay.
Press F on the screen, sir, on the keyboard.
Yeah. Is it? Let's check whether it is in a without full screen mode. Also, it is changing the slide.
Yes, it is changing now.
So it's going well as far as.
Yes, yes. This will be
uh,
fine. I find right. So if it's not in the presentation mode, and this will work.
Okay, fine. But let me try for the last time in case if
Yeah.
I start from beginning F5, should do I F5?
Yes.
Let me try once. Is it coming up in a full screen mode, sir?
No.
So I think better we go to that version only. Can I just keep it little bit bigger?
Yes. 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 It is changing now. Yeah.
Let me collapse if I can collapse this. I think this looks pretty well.
Yes.
Yes, sir.
Yes.
Okay. So I'm extremely sorry for glitch, but I hope now the slides are moving.
Yes.
Okay,
Yes, sir.
fine. Yeah, so I'm just reconnecting back. Sorry for that interruption, and I'm just quickly connecting back. So perhaps the discussion will follow in this chronological order, where we will discuss a little bit about the masonry, and then followed by its performance during the past earthquake, and then what are the various way of seismic evaluation as far as the masonry structure is concerned, and followed by some of the codal stipulations that makes us or that provides a certain amount of the earthquake safety against the earthquake or the safety against the earthquake as a force. And then obviously we will cover some properties and testing that required to be done for a masonry unit or masonry as a whole, that I will cover as a part of one of the case studies that we have conducted or the work we have carried out in our own department. And then of course some of the retrofit strategies that has been commonly employed in our own country and maybe the worldwide, and some of the challenges and way forward. Now the things is going well, sir.
Yes. Yes.
Okay, okay, fine. Thank you, sir. So these are some of the notable earthquake that I was discussing maybe a while before. This is the worldwide, some of the earthquake that has happened into the last decade, and a couple of them are very important or maybe more notable to us. Maybe this Nepal earthquake of 2015 and the Iran-Iraq earthquake that has happened on Iran-Iraq border region. And of course, Balochistan earthquake was also of a little significance, despite of their the fatalities. It has makes us a lot of lesson to learn. And if we look at some of the day-to-day activity, every day there will be a huge number of earthquakes that are appearing on our Mother Earth or on the worldwide. And there were yesterday 36 earthquake, magnitude ranging between 2.5 to 6.2. And of course, some of the important notable earthquake from Indian scenario is concerned, that some of them are major or the big earthquake that has been listed on the left side of this screen, and some of the earthquake of significance that has been listed on the right hand side. As I said, that this Latur earthquake, Jabalpur earthquake, and Bhuj earthquake that has completely changed our perspective towards the earthquake engineering, and our generation engineer have become much more motivated to work in the domain of earthquake engineering because of these three devastating earthquakes that we have seen in a span of almost 8 to 9 years. And coming back to the domain specific discussion, as you know that the masonry is one of the early day civilization artifacts that we have been using in the construction of obviously stone based pyramids, and then of course this masonry was used for the construction of the Great Wall of China. And obviously in India and Peru, some of the very well-known temples and the palaces that has been built either in a stone masonry. Most of the time they are in the stone masonry, and later on maybe some brick units that has been used along with the lime mortar. And in some Roman empires, there will be some amphitheaters and aqueducts and the colosseums, as we very well know, they were built either in the stone or later on maybe along with some kind of a brick units or some kind of the masonry unit. And these are typically possible to construct because such kind of the elements are very well suiting to the requirement of handling the vertical loads, which are always in the plane of the wall. But if any load which is out of the plane, perhaps they will become the most vulnerable element. But one of the major advantage of getting this masonry is that the same element performs different function in the same structure. It means it is acting itself as a structural element. It is also serving some functionality requirement. It is also giving some kind of the serviceability in terms of the fire, in terms of the thermal and acoustic insulations and the weather protection. And perhaps that was the reason why that masonry has been really considered to be the one of the very important element for the civil habitation in the old time. In fact, if you look at the masonry, then we know the masonry is assembly, is basically nothing but the assembly of the various structural units which are bonded together in a particular pattern by either mortar or grout. And there are different type of the mortar and the grout that we have been using, right from mud mortar to recent days cement, and there are now specialized grouts are also available for the construction of certain kind of the or to join the different masonry unit. But this masonry, when they have been used in a different form, they will form either they can be considered as a unreinforced masonry, or when we use and try to give a more strength of such unit in terms of placing reinforcement into the corners or reinforcement at a certain interval along the length of the wall, they become converted into a reinforced masonry. And there are certain part of the world they have been also employing a pre-stressed masonry. Of course, not very common in our part of the country, but some western world or some countries in the European territory, they have been using this pre-stressed masonry as well. As we know, the masonry structures which are very well designed for withstanding the compressive load, and they are able to do that because of the weight of the structure itself, and that's how we call them as a load bearing. And this load bearing structure is forming a perfect load transfer mechanism, or they are forming a very well transfer mechanism for load from horizontal to a vertical direction, and perhaps they have been mostly appropriately used for the building. And since they have been stable, they have been taking load, they have a good load transfer mechanism available, they have become a common building topology utilized in maybe a rural India as well as semi-urban area. However, if we look at some of the practices in semi-urban area, they have been mostly built with a heavy materials like the fire burnt red clay bricks or a cement mortar based blocks and reinforced concrete element using some well-established engineering practices, and therefore we can fairly treat them or we can fairly classify them as an engineering units or engineering building or engineered building, since we have been designing them using some engineering principles. But in rural area, it is not like that. In rural area, they are typically built with a locally available material like stone or lime mortar, and sometimes even a wood joist. Then they will be used and they will be typically built by the local artisans using their own experience and the local skill. And perhaps such kind of the building units which are being built with a local experience and local skill set, we perhaps call them as a non-engineered building. And perhaps they most of the time become little bit vulnerable as compared to engineered building, as we understand from the basic fundamental understanding of our engineering. But in urban areas, as we know that slowly and gradually this masonry structure have been decreasing, and right now the masonry has been considered as one of the infill material in the RC frame. So now the masonry has gone into a little bit shallower mode of just acting or serving the functional requirement of dividing the space, and of course we most of the time treat as a non-load bearing element, of course, but it is not true, as some of the research effort that has been showing since last 20-30 years. But now this red clay brick masonry infill is very oftenly replaced by now the AAC blocks and the fly ash bricks because of their distinct advantages and some of the issues or some of the reasons related to it. And therefore, we see as far as urban area is concerned, the technology is not very much inclined with what we have in a semi-urban and rural area. But some of the masonry unit that we have been very much using right now, that includes the red clay brick, fly ash brick, as well as AEC blocks, as you know that has been now very widely used, and fly ash bricks are also slowly and gradually replacing this red clay brick. And some of the other countries, there are different form of masonry units are also used, like concrete blocks. Of course, this is not very common in our India. We don't still build the concrete blocks. We either use red clay brick or maybe fly ash and AAC up to certain extent. And but in other part of the world, they have been also using hollow concrete blocks with the 2 cells or multi cells, like 3 cells or even more than that. So they have been developing the masonry unit of a different form. There are multi-cell also available, as you will be able to see in the next slide. There are circular cells based hollow concrete block, or there will be a square cell hollow concrete block. So some of the countries like Canada or even New Zealand, or somewhere in the European region, you will find out the practices of the masonry building, maybe not purely unreinforced, but they have been with such kind of the cells where you put a reinforcing bar. So these are the various structural unit or masonry unit that has been used. And as we know that the ancient structure were mostly unreinforced masonry structure, and typical unreinforced masonry structure is all started with a stone masonry. And some of the very well known examples are there, but except this pyramid just to start with in the Egypt, the others are the very much part in our own country. So as you can see, the Taj Mahal and some of the stone masonry work down the south and some of the masonry work in the north, they are all nicely been built and they have been used over a period of years. And you will also find out there are variety of the stone based masonry work that you will be able to see here, that some of them are very nicely placed, as you can see on the right hand side of the screen, that they have been nicely built. But this top portion you will be able to see that perhaps not very nicely built, but they have been very much part of our common human habitat. And some of the brick red clay brick masonry unit have been the part of the unreinforced masonry structure, where you can see there can be a multi-story building we could able to build, because of this load being primarily remain into the vertical plane. And you can able to see on this right hand side of the picture that some of the common practices, this may be the old construction, and the back side you can able to see very well accepted reinforced concrete element or reinforced concrete buildings that has been come up. But these are the very haphazardly done, and somewhere you can able to see a very long vertical red clay brick walls that have been built, and people have been living into that. Here also you will find out some of the again haphazardly built some of the red clay brick based buildings, and somewhere you will also find out the use of two different type of the masonry. I'm not sure whether you are able to see some cursor, because I cannot use my laser gun now, but are you able to see some cursor moving? Can someone help me to isolate?
Yes, sir. It is visible.
Okay, thank you, sir. So you will be able to find out that depending upon the availability and maybe some other factors, people have even started using the mix of the masonry unit. Perhaps it is not a very good practice, but you will find out them, and a different arrangement that you will also find out in a very simple unreinforced masonry structure in the different part of the India. And when this same masonry structure, when they built very nicely with a certain amount of the understanding, perhaps they were some of the best structure. And the left hand side picture is the very famous cellular jail in the Andaman and Nicobar, and it has performed very well during the previous earthquake. It is a two-story building, very nicely built, and still been maintained very nicely. And they have really performed very well in past earthquake. And some of the recent the exposed brickwork related structure you can able to see, or building you can able to see. Of course, IIM Ahmedabad is one of the very iconic structure in Ahmedabad. But apart from that, there are so many other part of the country and some other cities. We have a very nicely built masonry based structures, as you can able to see. Of course, it required a little bit more detailing, but they are looks very composed, very solid, very stable, and very nice and elegant in its appearance. And some of the worldwide practices, if we look at, perhaps they mostly give a lot of importance and the weightage to a reinforced concrete, because most of the Western world, they have been using the hollow concrete blocks or hollow masonry unit, wherein they can put a reinforcement and then they can be grouted. So you can able to see this wall on the right hand side, where you can able to see there are horizontal reinforcement bad joints, as well as in this picture you can able to see a vertical reinforcement that has been utilized in order to make that element as a load bearing element. And you can able to see on the left hand side that a complete four walls that has a vertical reinforcement and also have a some horizontal reinforcement in certain course. So this is a very important part that the other countries have been used. Perhaps they do not use like what we use in our own country. And of course, recently we have come across the latest topology in terms of the masonry structure is a reinforced masonry structure, but in a different way. Typically, every structure or most of our reinforced concrete structure, we build the RC frame first, and then later on it is been infilled by a masonry. But in confined masonry, the process is little bit reverse. It means you build both of them simultaneously. So you build the masonry structure up to certain height or up to the height required, and along with that, you also have a reinforcement going on at a regular interval. And then you also cast the reinforcement element little bit later, once you have the masonry walls being constructed. So they itself act as a framework, and you require a minimum formwork when you are at the junction, or somewhere in between, you required a very minimal formwork, because at least two sides have been already act as a the masonry wall act as a formwork. And that's how it becomes a very easy to construct. But of course, sometimes it has its own challenges, but it becomes a very important way of constructing the confined masonry structure. And because of such both element available for a building like the masonry wall, along with the some of these element reinforced concrete element, we can go up to at least a 4 to 5 story vertically upward as far as masonry structure is concerned. Otherwise, if we look at our own philosophy of masonry structure, we typically do not have a much examples available where we have built the masonry structures more than 2 story without any reinforcement. So the unreinforced masonry structures, they may be mostly a 2 story, limited to 2 story, but with a confined masonry, one can go up to 4 story or 5 story construction as far as this philosophy goes. And some of the recent example in the city of Ahmedabad is IIT Gandhinagar campus. So this is the construction, confined masonry construction, through which the entire IIT Gandhinagar campus has come out. Some part of, at least the hostel of this IIT campus, and some of the faculty residence building that has been come up with a confined masonry concept. So wherein you can see that the brick wall has already been taken up, and here in all, the IIT campus being a green campus and Griha rated sustainable campus, they have used the fly ash instead of red clay brick, and therefore you will able to find out that in order to utilize this waste in terms of the fly ash, they have prepared the fly ash brick on at the campus or at the site, and then they have been using that as a masonry unit, and they have been building the in between the columns with a two-thread connection as far as the giving the confinement to that wall is concerned. And you can able to very well able to see there are 3 or 4 story buildings that are coming up with a confined masonry. And these are some of the recent practices that we see, and overall the unreinforced masonry structure that either have been built or perhaps still we are continue building. But if we look at and try to understand from engineering perspective, then masonry structures are typically passive structures, and therefore they heavily depend on its mass and stiffness property. And of course they are very good against in own plane loading, as we have just discussed, but their out of plane behavior is very weak, and therefore they are vulnerable to lateral load which induced or applied in out of plane to certain walls. Of course it becomes in plane loading to certain walls, but for certain wall it becomes an out of plane loading, and there where it becomes vulnerable. And because of their such vulnerability, the in past earthquake we have experienced worldwide that the masonry structures become vulnerable, and they have undergone damage of varied degrees, and that damage includes from partial damage to a complete collapse if that particular structure is not very well built, and they have not enough earthquake resistance features, then perhaps they are likely to undergo complete failure. That we'll see in some of the photographs little bit later. And if we look at the past experiences and our learning from our past experiences about the seismic performance of masonry building, then obviously when any structure undergoing a complete collapse like one which is which I am showing right now, which is nothing but various bungalows during the Quetta earthquake of 1935. They have been completely raised off or completely collapsed because of their poor resistance against an earthquake. However, you can also able to see some of the structure adjoining to them. They are under construction and they are still standing, but some of this old construction that has completely devastated or completely collapsed under a seismic excitation. And this is the photograph from 1993 Latur earthquake, where you can see a masonry building is completely red clay brick based building has completely collapsed. And when any structure or any masonry structure completely collapse, we cannot do anything except we have to recreate it. But some of the structures does not go a complete damage, or they does not completely get collapsed, but they show the damage of varied degrees or different forms due to the mass and stiffness attribute of masonry structure. So some of them I have tried to list it out here in some chronological order, and the some classification that I have tried to maintain here, so one can understand that most of the masonry structures are found to become very weak against the out of plane bending. So as you can see, this is one of the long building with a very long walls with a height also huge. So this aspect ratio is very large, and perhaps that makes them this long wall as a freestanding wall. And under the lateral component of an earthquake, the complete wall has undergone a flexure out of plane bending, and because of that out of plane bending, the masonry wall, as we know, which is very weak in tensile stresses. In fact, we don't consider any tensile stresses as far as the design of masonry wall is concerned, because the tensile strength is very low. They are almost of the even of the order of maximum 1 Newton, 1 MPa, or sometimes even less than 1 MPa. So therefore, they're likely to fail as and when there will be a out of plane bending, and that is what is evident in this some of the masonry structure as we have seen in the Quetta earthquake. Similar kind of the failure that you will also able to see in a Chile earthquake, where you can see that this long standing wall with some partial stiffness. As you can see, there are regular stiffness as you will be able to see into the wall, but still the in between piers that have become huge in aspect ratio, and therefore it makes a perfect case of the long pier subjected to lateral load, and therefore it is likely to undergo out of plane bending, and one can able to see there will be a tensile failure appearing into this particular wall. And this is a very perfect this is a very good example of a out of plane wall failure. This is the some of the recent pictures taken from the Nepal Gorkha earthquake of 2015, where you see such a massive stone based wall, two massive stone based wall with some internal partitions. They are not they are just partitions or the division of the space, and therefore this wall become from one end to another end, such a huge long wall with a huge almost 2-story height. They become like a completely freely standing, and you can see it as completely over toppled or overturned because of the out of plane bending. And you will be able to see that that it has completely lost its junction from the cross wall. So you will be able to see that it because it has started losing its connection from the cross wall, it has completely collapsed because of the bending in a out of plane direction. And such kind of the failure was very typical in the Nepal earthquake that we have seen. But similar experiences that we have gained in the 2001 Bhuj earthquake as well, wherein you will find out sometimes not only the out of plane of a long wall, but sometimes even a short wall, they may go away from the corner. So because of the weak connections of the cross wall, you will find out that it has completely gone from the corner of the building. And because that corner has gone off, despite this stone structure or the stone building has a continuous lintel, as you can able to see. I hope you are able to see some of the arrows which I am moving, because there was a continuous lintel. Perhaps that was some engineers who have already realized that there is a requirement of a continuous lintel, but that continuous lintel has also collapsed because of the corner wall has collapsed. So that was a typical corner failure that we see in the Bhuj earthquake and in some of the old earthquake as well. Again, if we look at when the component of the earthquake get transferred in an in-plane direction of any wall, you will find out that because of the again aspect ratio, you will find out that some of the piers are typically undergoing a shear deformation. So for a certain aspect ratio, your shear deformation becomes very predominant. We all are very well aware that any freestanding wall subjected to lateral load, they are typically undergoing both type of the deformation, both bending deformation as well as shear deformation. And we have found out that if we have a certain aspect ratio less than half, then perhaps you will find out the shear stress become very, or shear deformation becomes very predominant, and that will lead to some diagonal kind of the failure into a building. So as you can able to see here, there are regular openings, and that allows the formation of piers with a certain aspect ratio. And as you will be able to see, they are almost close to one or little bit higher than one aspect ratio, and they have undergone a huge shear deformation. And because of that shear deformation, you got a diagonal cracks in the series of that particular long wall. And that was happened under a earthquake of magnitude 7 in 1979. Some of the similar pictures or some of the similar behavior we have also seen in Bhuj 2001 earthquake, where you will find out that a shallow wall with a regular openings undergone a first shear failure, and later on you can able to see they have completely collapsed because of the very low strength of that particular wall. And here you will be also able to see that the somewhere you will find out they have been not completely made from a masonry unit. Sometimes they also use a stone masonry. So the stone further connected with a limited limited options of mortar, maybe mud mortar or maybe lime mortar, or nowadays we also put a cement mortar also, but because of the brittle nature of that wall, it completely get collapsed. So these are a very common sight during 2001 Bhuj earthquake, and before that in Jabalpur earthquake also we have found out that despite we have a very good aspect ratio of the wall, you will find out with the opening, close to the opening, there will be a diagonal cracks at the top of the opening as well as bottom of the opening. You will find out there is a diagonal crack because of the shear. So such kind of the site is very common, and of course similar site you will also find out in a Nepal Gorkha earthquake, wherein you can see this is a two-story building, and this wall, which is subjected to a some component of earthquake in the same direction, becomes in plane loading, and because of this pier aspect ratio of the pier, it has completely undergone a X kind of the failure, which is an example of a shear failure in the unreinforced masonry wall. And when this aspect ratio becomes little bit higher as compared to previous aspect ratio, you can see here there are a little bit larger aspect ratio, and there is some beam going on, and again there will be some height of the building or some distance available as far as this building is concerned. So this will act like a fixed end connections for a frame with a little bit larger aspect ratio, where you can able to see a completely a wall flexure happen, where you can see that some of the tension appears on the bottom side of this wall, and because of that you will find out that some of the masonry or some of the plaster work has already gone, and there will be some cracks which has been gone right from tension to a compression zone. So it is a very typical of a flexural failure, even in case of our reinforced concrete flexural element. So you can able to see that the tensile cracks grows from the tension side and penetrate full up to a compression zone. And some of the other typical site that has been seen in some of the earthquake, that has also been shown here, but now with some classification and some summarization of the types of the damages, and you can very well correlate that here a long standing wall which has completely undergone a vertical overturning because of the outer plane, as it is listed in some of the damage classification by D. Alaya and the Speranza. They have given a different kind of the classification for the type of the damage, but this is very much related to a type of the classification, and here you can able to see it has partially come up from the junction, and therefore you can also understand that it is falling into this category of overturning with a one side of the wing. So you can see one side of the wing has completely come out, but there can be a both side of the wing can come out, or there may be a corner failure as we have seen earlier, or there can be a partial overturning, or it can be a vertical strip overturning. So these are some of the classification that has been given in the source which I have mentioned here based on some past earthquake. And if you look at the all damage in a one go, that was summarized in the book of Temezovic, where you will find out that all those piers under an earthquake, when they will subjected to in-plane loading, they will undergo a shear failure, as you can able to see. And this wall is definitely undergoing both shear and flexure. So when shear will become predominant, you will get a X type of the X type of the damage, and when they will undergoing the flexure, you will find out there will be a some tensile failure happen on this part. And when any wall which is perpendicular to the direction of the seismic excitation, they will undergoing a out of plane bending, and because of that out of plane bending, you will find out there will be either that wall can be over toppled, or it can undergo a tensile cracking, and it will start and completely get penetrate right from top to the bottom. And it is also found out through some past earthquake experiences that for a multi-story building, this out of plane vibration of wall become found to be magnified, or found to be much more pronounced as you go from lower story to a higher story. And this we can very well understood from the principles of the dynamic, as we know that when any building is vibrating with a lower mode of vibration, typically your higher stories are always undergoing a large deviation or large displacement from its original static equilibrium condition. So any multi-degree of freedom system with a lower mode of vibration always shows there is a higher participation happened from the top stories, or from the top a couple of stories, depending upon the mode. So this is what the people have already been summarized, and based on some of the studies that what we have done, we have now summarized some of the damage pattern which we typically observed during any earthquake. So they are typically an out of plane collapse of exterior wall or any interior wall as well, failure of the wall corners and the cracks at the wall intersection. That can be another common type of the damage pattern that we see. There can be a diagonal cracks in the structural walls, predominantly when the in-plane wall is undergoing the shear failure. Then you will find out a diagonal cracks in the wall, or when the aspect ratio is little bit higher, because of the lateral loading, the wall can undergo wall flexure, and they will also lead to a cracks in the spandrel beams and or parapets, which is available towards the exterior wall. And there can be a partial disintegration or a collapse of the structural wall, and last but not least, either partial or a collapse of the building. So these are the some of the sites or some of the observations that we, or some of the past earthquake learning that we have tried to summarize. And most of the time, irrespective of various event that has happened over a period of time or over an interval of time, the masonry structures will more or less behave, or they will subjected to the failure any one what is been listed over here. And therefore nowadays there is a recent practices, as we find out somewhere, that there are certain buildings who put up precautionary measures, or they put some wall stamping, and what they typically write something like that, as some of the building in California and some of the URM building in Portland, they have already been mentioned that it is an earthquake warning. This is an unreinforced masonry building. You may not be safe inside or near unreinforced masonry building during an earthquake. So perhaps this may be a little bit new addition into the practices when you build a URM. But that also gives the idea that people are still do not want to discontinue of making and constructing the URM. So there has been some affection, there has been some utilization of the URM, but now they are also putting a earthquake warning as some of the examples that I have showed here. So these are some of the experiences that we built, and when we start looking at some of the damages, perhaps we try to understand that, and we try to build some engineering about it, and that will allows us to now typically take up a seismic assessment of or seismic evaluation of the masonry building. So typically, the seismic evaluation is nothing but to understanding that how that building, the attribute, what was the attribute of the building, what was the load transfer mechanism, what kind of the damages it has undergone, and based on that, we try to figure it out that whether this building has lost its integrity to a varied degree of levels. And once we are able to establish that no, this cannot survive for more number of years, or the residual life of that building becomes now very less, perhaps we can take a very very well thought of decision whether we want to discontinue the use of that masonry structure, or whether we want to increase the capacity of the same structure by doing some retrofit. But that required a certain process to be done. That such kind of the assessment or such kind of the evaluation, that required some scientific and logical process to be followed in order to further increase or improve the usable life of the masonry structure. And over the period of the time, because of the experiences and the various work that has been carried out by various researchers all across, or by various agencies all across, now the seismic evaluation has been taken a formal approach, or they have gone a very formal approach of doing that in a three phase. So typically any seismic evaluation of masonry building, and for that matter, not only masonry building, for any other type of the building, maybe reinforced concrete or even a steel building, but all they are typically follow the very similar kind of the process, and that process are divided into three phase, and that three phase include the phase number one, which we typically is the RVS method, rapid visual screening, which allows us to understand the basic attribute of that particular structure. So we need to go to the field. We have to undertake a visual inspections of that particular structure. We have to write and we have to build certain forms. So there are different type of the forms that people have generated, or some agencies or some of the stakeholders have generated a different type of the RVS depending upon the requirement, but basic philosophy remains same, that we try to understand at least the basic attribute of that particular structure. We want to see what kind of the damage it has undergone, and there will be some other relevant piece of information, that how old that building was, what was, whether that building was in utilization or not, and what was the occupancy, whether there was any visible damage or pre-damage state was observed or not. And there are so many other piece of information that we'll try to collect through RVS method. And then there are different classification method that people have developed, and they have given some kind of a rating system also. And of course, there is no unified method available in our own country at this instant of time, but there are certain countries like Canada, New Zealand, they have a rating system in place. So they give a different type of the rating at the end of this formulation of that form. So after forms, you take a different kind of you assign a different type of the rating, and based on the rating, you can take up the further decision. In New Zealand, in fact, they give a color coding also. So along with the rating, they use a different color coding, and they paste this color on the structure itself. So anyone can understand, okay, that this building, whether it is safe to use or not safe to use, or they need to be required to be retrofitted or not. So such kind of the various kind of the RVS method and different kind of the seismic evaluation as are in place in the different part of the world. But typically this RVS plays a very important and basic step to conduct the seismic or to carry out a seismic evaluation. And then the second phase is little bit more on a scientific approach, in the sense that we try to get hold of some more reliable assessment or reliable piece of information in terms of the structural drawing, whether they are available or not. And we are very well aware that in old structures which are at least 20-25 years old or maybe 50 years old, it is very difficult to get hold of the structural drawing, and therefore you have to heavily depend on the structural details available in front of you. And many a time certain structural details are not available because of the alteration into the structural system, or because of the non-availability of the changes that the structure has undergone. So these are the few challenges that we will face when we take up a preliminary assessment. And obviously we will now need to calculate whether what different kind of the load that has been considered while designing this particular structure, and whether the structure has enough strength or not from a basic calculations that we carry out in the preliminary assessment. And then comes a third and very important part, which is called detail evaluation. The detail evaluation consists of two further subcomponents. One is called in situ testing. So many a time, because of the non-availability of certain piece of information, we are not able to find out, or we are not able to get certain input data. So in the absence of such input data, we need to rely heavily on the NDT. So there are certain methods even available for masonry structures also, which comes under in situ testing called non-destructive testing, and obviously there will be a semi-destructive testing also. So now we go and try to build such kind of the input data from either conducting NDT or semi-destructive testing on the structure itself. And then with this input, we'll try to further work it out with some advanced level of seismic analysis. Either we perform a pushover analysis in the form of nonlinear static analysis, we carry out a dynamic analysis, both the linear and nonlinear dynamic analysis, and then sometimes more sophisticatedly, we carry out a finite element based method to find out what will be the current status or current strength of that particular structure. But as I just said, that biggest challenge when we take up all this advanced seismic analysis is the input data, which heavily depends on this entity. And therefore, the reliability of such kind of the testing becomes very crucial component when we try to figure it out and try to apply this advanced seismic analysis. And we have been facing a lot of issues related to that. But just to show you some of the RVS form, of course, this is not the unique RVS form. There are different type of the forms that has been evolved, but one of them looks like similar like this one with a reference or the source available here. But if you look at the left hand side, typically it shows all the three phases, part 1, 2. Of course, 3 is not very much here, but part 1 and 2, phase 1 and 2, which includes the field survey for rapid visual screening RVS, and then you carry out a preliminary survey of the building based RVS score, and then in order to get a modeling of the building, you have to carry out a preliminary analysis, and then you have to carry out a detailed analysis. And once you are done with the detailed analysis, you lead it to development of fragility curves or a risk assessment, and then you establish what kind of the hazard that your building is subjected to, and perhaps then you lead to a recommendation whether you want to retrofit the structure or you want to rebuild the structure. So typically this flow diagram shows one or the another way all the three methods with that we typically follow as far as the seismic evaluation is concerned. And as I said, when it comes to a detailed evaluation, mostly we do it in a two-way, and out of this in situ testing is playing a very important part. And perhaps as a country, we might not be still capable enough to conduct this kind of the testing, or because of the limited set of skill available, or because of the limited people who grossly involved in such kind of the thing, there is always a dearth of input properties or input data as far as this detailed evaluation is concerned. And of course, we have been struggling all the way, right from getting and employing the right kind of entity, getting up the required input data, and then carry out the detailed evaluation in terms of the analysis. But just to share with all of you, there are different in situ testing of masonry building as of now there that we employ. That includes the non-destructive testing, which includes the rebound hammer test and UPV test. As we all are aware that this rebound hammer test and this UPV are more suited to a concrete structure. But of course, if we try to employ for a masonry structure, it is possible, but there is always difficulty to calibrate the rebound hammer for other materials, and therefore there will be a little bit of hesitant. There is a little bit of skeptical about the use of the rebound hammer for the masonry structure. And the same goes with the UPV because of the heterogeneous nature of the brick, and as well as the overall masonry with a mortar which is made from a different material, brick made from a different material. The UPV tests are also non-reliable. So most of the time, these two tests, which are very important and vital tests for a concrete structure, they are typically not very well available for a masonry structure. However, there are certain other type of the entity that are typically being used, and of course some of them are still not into the reach of a common engineering field or common engineering practices, but some of them can be used like impact echo to calculate or to find out what are the various location of the void areas into the masonry structure. And then one can also go to the infrared thermography, which is nothing but the digital imagery in the infrared spectrum to determine the extent of void area, as you can see on the right hand side of the figure. And now people are also doing the radiography to detect the reinforcing steel or bed joint reinforcing steel, whether they have been there into the wall or not, masonry ties or anchors, pipes, conduits, anything that we want to figure it out, then we typically do this radiography. Of course, this all set of instruments are a little bit costly, but they have been developed by some of the developing countries, and they are available. Of course, costly, but somehow they are available. But the most common type of the test, which is not the part of a non-destructive test for masonry structure. So typically we realized over a period of time, and people have realized that to carry out NDT for masonry structure is not a very viable solution, or it is not feasible all the time, and therefore there will be some semi-destructive testings are required to be done, and they are typically done by a different way. So one of them is called flat check test, which is following as per ASTM C1196, and this is typically used to calculate the in situ compressive strength and the stiffness of the masonry, where you have to open a bed joint at two different level, and you have to place the flat jack. They are available in a different shape, either rectangle or maybe a semicircular, to get it adjusted in a different form of the masonry. But you need to open out a bed joint, you have to insert that, and then you have to pressurize it to give some amount of the load, that prescribed load, and in between these two you have to place your LVDTs, or either mechanical dial gauges, both in vertical and horizontal directions, to figure it out what is the strain produced into that particular element, and you can develop a stress strain requirement, and you can calculate at what load what would be the strain that is happening, as well as you can also calculate what is the compressive strength of the existing structure. So this is very well established, very common test that people are doing, and there are certain organizations in India who have been doing such kind of the testing very regularly in India. Just to share with you, is one is CSIR SERC, and another one is CSIR lab of IIT Roorkee, which is CBRI. So both of them have such kind of the facilities available, and they have been doing such kind of the flat check test. Of course, they may not be in the reach of the other stakeholders in the other part of the country, but at least some of the organizations they have it. Some of the IITs also have such kind of the testing facilities available. Typically, maybe IIT Kanpur, IIT Guwahati nowadays, and IIT Madras, they have such kind of the capabilities. The another important semi-destructive test is a shear strength test, which is performed by opening the brick along with the bed joint and making a certain space, and then putting a jack, and on other side of the brick you are measuring the deformation. So this is very similar situation like a direct shear test in a geotechnical engineering, but there are to be done on a wall itself. So you have to open up out some of the space along with the joint mortar bed, and then you have to apply the force, and then you have to measure that what is the lateral deformation that this wall is undergoing, and that will determine what is the shear strength, in situ shear strength of the masonry. Of course, the shear test is always been difficult. We have our own experiences when we try to do it, the shear strength of the wallets in our own lab, and doing as per ASTM. It becomes always we have to be very careful in establishing this shear strength. But apart from that, of course, this is in situ semi-destructive testing, but on laboratory scale also you can do a diagonal test as per ASTM. And we have a very well specified ASTM proceedings to prepare the wallet, and then we have to apply the load either horizontally or vertically, and we have to measure the displacement along the vertical, or it means diagonal direction of this, and then we have a equation developed for that, from where you can calculate the shear strength. But this is in situ shear strength I'm talking about. The other important and very interesting test, semi-destructive test that people are doing and some other part of the country have been regularly doing, is flexural or tensile strength test as per ASTM C1072, which utilizes the bond branch apparatus. As you can see, the basic principle is to use a lever arm to apply the force and to figure it out that what is the bond. So sometimes see, this bond branch apparatus is typically used to measure the bond strength of the masonry. So these are typically done at laboratory level on the prisms of the brick masonry, or they may be also done to calculate the in situ strength of the existing masonry. As you can see, you have to open up some of the area, you have to open up the mortar joint, and then you use this wrench and try to figure it out that what would be the force you have applied and what would be at what load this has completely lost its connections, or the bed, the joint has broken up because of the applied moment. So this is also very interesting but very important in situ test you can do. And of course, this slab load test is allowed as per IS 456 and ACI code of 357, where the structural integrity and the load carrying capacity of the slab can also be obtained by just putting a load above the story and measuring the deformation at the below story. So these are this couple of pictures that shows both the loading on the above part of the slab and the measurement at the below part of the slab. Of course, these are a very like regular feature. We have seen that commonly people also employ such kind of the testing to find out the slab load test even for masonry as well as RC structure. So these are some of the in situ testing that we carried out. Of course, I have avoided the advanced seismic analysis as a part of detailed evaluation, because most of you might be very well aware that once we have an input available from such basic tests, what is the shear strength, what is the compressive strength of the masonry, and obviously the third and very important element and the parameter which is always difficult to get and which varies very hugely across the various part of our own country is the modulus of elasticity. So establishing that modulus of elasticity and its relation with the modulus of rigidity itself, of course, sometimes a challenge, as we have learned from our own experience when we try to get it in our own laboratory. We find some of the challenges, but as you are very well aware, the modulus of rigidity is almost around 40%, 30 to 40% of the modulus of elasticity. But getting that also is very important. And once we get hold of such kind of the basic information for an existing structure, we can apply them into the our any of the methodology. Typically, mostly we use this non-linear static analysis or a pushover analysis, and then we start understanding that at what stage that our structure has gone. So that I have, of course, I have avoided. I have also avoided some of the mathematical equations intentionally, so that we can convey the basic fundamental understanding about this masonry structure. But anyway, once we know this kind of the basic properties, the mathematics can be very well developed. Mathematics can be very well done. There are very good references are available in terms of the books and certain literature which talks about how to use that mathematically. But these are some of the basic piece of information and some important important testing, experimental testing, either on in situ level or maybe at laboratory level that we have to carry out. And once we are done with this, at least we can try to better understand the seismic response of the masonry structure. And as we are very well aware that the whenever any masonry structure which is has a typical component in terms of the roof walls and the foundation, and the load which are coming in vertical and horizontal directions are getting transferred from roof to the wall and wall to the foundation, and therefore certain walls under an horizontal force, they will be act as an in plane, and some of the as an in plane loading, and some of the wall will be subjected to out of plane loading. And the major problem we face in masonry structure is that they have a very good in plane loading capacity, but they are very weak against the perpendicular directions of that wall, or the when earthquake is applied or lateral force is applied perpendicular to the plane of the wall, where it is either likely to undergo the overtoppling, or depending upon the boundary, if it is a freely standing wall, it is obviously undergoing toppling. But if it is having a different boundary conditions like fixity at both at top and bottom, it will undergo a bending or flexure, and it will typically converted into because of the weak tensile strength, it will immediately get into two pieces in the out of plane direction. And if we talk about any masonry building, and if we take a different wall like A and B, and if they are not been very well connected in by a cross walls, then under an event of an earthquake, both that wall which is perpendicular to that earthquake loading, they will likely to overtopple. And therefore, in order to survive or in order to get a better resistance from any masonry building, we have to have a box type of the actions, or we have to have a unified action. And unified action in terms of that the cross wall should be supporting this perpendicular wall. So we have to ensure wherever in whatever masonry structure, if your cross wall is supporting nicely to this perpendicular wall, perhaps their behavior may be much better. And of course, we have seen in some of the earlier part of presentation, some of the pictures, that even you have a cross wall, but there is no proper connection between these walls, then this a wall which is perpendicular to the direction of the lateral load will either overtopple or they will overturn from the place. And therefore we must have to have a bonding, very good bonding between the both perpendicular walls whenever there is an earthquake. And of course the aspect ratio also plays a very important role. So even despite we have a cross wall available, but if we have a very long wall, then obviously because of the good support from the cross wall, this is likely to undergo a bending. So therefore we have to make sure when it comes to masonry structure, they have to have a better aspect ratio. And as we can see that for a short wall, you will find out that the cross wall is very well supporting the wall which has a lesser aspect ratio. And therefore they have a better load resisting capacity, because their behavior become converted from the flexural to a shear way of undergoing the deformation. And similarly, there are certain understanding we can get that under a lateral loading, that if we have a 1.5 brick wall, and against of that if we have a thin wall of one brick, then this wall with only one brick is likely to undergoing a bending or flexor or overturning. And similarly, if you have a short wall of one brick and you have a tall wall of one brick, same brick, but then they have a different length, then also the long wall is likely to undergo overtoppling. So you have to have a better aspect ratio for the wall. You have to have a basic dimension done for both kind of the situation where we have a thick wall as well as where you have a long wall. So you have to make sure that the height to length of the wall should be well within a certain limit in order to make them a better earthquake resistant. And why we are talking about this a lot, because typically we found out by our own experience and as reported by many other technical references that the most of the time the fundamental period of the masonry structure is around zero point 0.3 second or even less than that for low to medium rise building, because of the presence of many structural walls. Okay, and because of this presence of many structural walls, this structure will become stiff, and the stiff structure always attract larger acceleration, and because of this larger acceleration they're likely to undergo more damage. And therefore because that the time period of such kind of the masonry structure is very very low, and almost it becomes an acceleration sensitive structure, you will find out even a moderate earthquake can also cause a lot of damage into the masonry structure. And therefore the masonry structures become little bit vulnerable against a different variety of the earthquake. As you are very well aware that large or big earthquake definitely have a huge frequency content, and therefore they will likely to affect the majority or vast different typology of the structures. But even a moderate earthquake can also cause a failure or cause a damage to the masonry structure, because the low to medium rise buildings are always considered to be a stiff structure. And therefore in order to avoid such kind of the failure in a moderate earthquake or even a low or the very frequent earthquake with a lower magnitude, we have to have our masonry structures very well built with a certain earthquake resistant features. And therefore we are fortunate to have a code of IS 4326/1993, which is earthquake resistant design and construction of the building, which has given a lot of codal stipulation in order to save the foundation failure as well as to prevent the failure of the structural walls and the other structural element of the masonry building. So of course, I am not going into very much detail of each one of them, but some of the important aspect or some of the important elements that has been addressed by IS 4326, they are foundation, and there in foundation we have to be very careful about the liquefaction, and number two, that the foundation should not be get lost under an event of an earthquake. Otherwise, you will find out that there will be a the failure of the structure as a whole, and therefore most of the time we will try to see and we make sure that the foundation should not be founded on a loose soil which can subsidize or liquefy, and therefore we have a lot of ground improvement techniques, and there is a lot of geotechnical earthquake engineering and that take care of such kind of the things. But as far as structural engineering is concerned, we have to be very ensure, or we need to ensure, or we have to be very sure about the separation of adjoining structures. So we have to categorize our building depending upon the importance factor as defined by the IS 4326. For a different seismic zone, we have a different category of the building, and there are different requirement that has been placed to make sure that there is a enough separation for the adjoining structures. So here we need to realize that the structures with a different total height or story height and different dynamic characteristics need to be separated, and perhaps many of you are very well aware that this is done in order to save our structures to undergo ponding effect, because two dynamically different structure is likely to undergo a different mode of vibration. So you are very well aware from the concept of the dynamics. You can understand that a different dynamic characteristic under the same frequency likely to undergo or excite in a different vibration mode, and therefore you will find out when you try to draw the mode shape of that particular building, and if you will find out that one of the building is vibrating in the first or second mode while other building is vibrating in some higher mode, then there may be a collision between these two structure, and therefore we need to have some separation of the adjoining structure, because we are very well aware that this masonry, unreinforced masonry structure, they are typically been developed and they have been constructed in our country very haphazardly, and therefore this particular provision makes a lot of sense. And as far as to ensure the good cross wall connections, the IS 4326 talks about a two-third joint. Of course, they have some difficulty to be observed during the construction of such kind of the two-third joint. In fact, some of our experiences or some of the feedback that has been received during this confined masonry construction also, that this two-third joint is really a little bit difficult to adhere or to maintain a quality as far as the construction is concerned, but they will be really very important element to stitch the both the walls together, and therefore we need to provide some kind of an alternate two-thread connection as detailed in IS 4326 for a different cross wall. So you can able to see that whenever it is a two end wall are meeting, you have a different kind of the two-thread connection. When there is an internal wall meeting to the long wall, you have a different kind of the two-thread connection. So there is a different detailing that has been given as far as the masonry wall is concerned into the IS 4326. Apart from that, there are certain restrictions to provide the opening so that there can be a formation of piers, enough piers with a good enough shear resistance that can be obtained. So therefore, the IS 4326 has also given a certain dimensions or restrictions towards the opening for masonry structure as outlined in the table number 4 and as given notation in the left hand side of the figure. So you have a different openings or restriction into the opening to ensure that the column I mean to say the wall has enough piers available between the opening. And similarly, of course, this is very difficult to do. I also do not have a confidence of doing this even if I have to practice, because this is a very small two-thread connection adjoining to the opening. But instead of that, there are so many other countries code allows you to put the reinforcement on the all four side of the opening to make sure that there will be no shear cracks propagate from the sharp corner of the opening. So of course in 4326 they are still advocating some toothed connection to be used along with some corner reinforcement. So there are they have specified as corner reinforcement but along with the toothed connection, but it is a little bit difficult to practice in the real field. But this is what the stipulations, or this is what the features that 4326 has given. And apart from that, there has been a requirement of shear strengthening arrangement for D and E type of the buildings. Mostly the D and E type of the building are the building. They are located in a highly seismic region as far as they are mostly configured into a non-engineered building. And therefore, there has to be a certain kind of the features that mandatorily to be done as far as IS 4326 is concerned. And mostly you will find out as it is given in the next slide that there are certain table who recommend the use of the band. So you have to provide seismic band. So as you can see in this picture that we have to provide a seismic band at the top of the just below the roof level or at roof level. Also we need to have a continuous seismic band at the lintel level. Of course, we are not providing or the IS 4326 does not advocate the use of the seismic band at sea level also because of the door opening. But some other code also allows the use of a seismic band at the sea level. And later on you will be able to see that some of the experiment done in our university that shows efficacy or the effectiveness of use of a seal band also. But the RC band details are also been provided here. Of course, I'm not going into very much detail of all those categories of the building and what kind of the requirement. I think we can very well understand from it. But a different kind of the geometry and the cross-sectional wall have a different kind of the detailing as far as RC bands are concerned. So these are the some of the corner reinforcement that we have to practice in order to save the corner crushing of the walls or opening of the walls that has been mentioned here, and some kind of the lateral ties that we have to use with a different depth of this band. There may be 75 band or 150 band. They have a different detailings that also been given in IS 4326. And typically nowadays, at least to share with you, I have seen some of the practices, good practices, where people are doing such kind of the thing when they build a masonry structure, which is a good part of it. But the most important but not very well used feature of IS 4326 is a vertical reinforcement detail. 4326 in 1993 has also outlined the use of vertical reinforcement, maybe because some other countries they have a common practice of using this vertical reinforcement because they have been using a hollow concrete block. But in our own part of the country, we never use such kind of a hollow block, and therefore we do not use vertical reinforcement. But IS 4326 has outlined the use of vertical reinforcement, and this vertical reinforcement for a different thickness of the brick walls that need to be placed in a vertical direction with a pocket, and that need to be grouted with a cement based mortar grout. So they have given a different grade of the mortar grouts. They have given a different reinforcement diameter to be used for a different thickness of the wall and different location across the different type of the bond. So as you can able to see that with a small thickness, they are mostly close to the corner of the both cross junction of the wall. But when you have a big thick wall, they will be almost reaching at the center of that particular wall, and from there you have to pass on a vertical reinforcement and you need to grout them. So these are some of the provisions of IS 4326 which are still very easy and commonly been required to be employed. and they are definitely not very difficult, because some of the building models that we have developed here, we have used such kind of the vertical reinforcement, so they've been really easy, not that that difficult. But there is another code in 13 in the form of 13828, which is nothing but the improving the earthquake resistance of low strength masonry building. So that there is another code which talks and emphasize more on the shear type behavior for a masonry structure. So they are emphasizing the use of three different elements and three different actions to be ensured in any masonry structure. One is a shear wall, which is, it means you have to have a good enough in-plane capacity of the wall. You have to have a structure acting as a box type, and number three, that you need to create such kind of the box type of the action by a regular use of the band. And obviously this need to be read in conjunction with the 4326. But as I earlier also shown, and I have shown in some of the photographs also earlier, that any masonry structure will be behave nicely if it will be act as a box type, or it has a box type of construction. And this is very much important from a stone masonry element, because in stone masonry you will find out that under the lateral load, the stone masonry, which is nothing but made from a random rubble stones, they're likely to go away from its position, and in order to hold them, you required, and it has been given in the form of a codal provision, you have to have a through stone. It means a stone which has almost a width equal to the thickness of the wall, which is holding and dividing this entire wall into number of small walls with a different height. So if I just try to see if this is the elevation, and if you are using a through stone, the total vertical height may be 1.2 meter. But now, because of the use of the through stone, the vertical height is converted or limited to only 600 mm, and therefore it will improve a huge shear strength of that particular wall. So such kind of the detailing was already given in IS 1382 19383. Of course, we do not have a very good manuals and the other documents available in our country, but there were a few references for seismic retrofitting of masonry buildings were made available after 1993 Latur earthquake. So after Latur earthquake, there were some government agency who become instrumental, and there are certain private stakeholders who have been instrumental to give a certain earthquake resistant guidelines for a masonry structure or a low strength masonry structure. So this is one of them. Of course, it is not only the one, but this is one of them which is coming from the government. And if we typically look at some of the seismic retrofitting of the masonry building, then one of the very basic way of doing a retrofitting of any masonry structure is the use of a seismic band. And this seismic band may be either in the form of a reinforced concrete beam with a reinforcement, or it can be in the form of a timber band. So in the hilly regions, or in some of the regions where still people are using a wood, or the wood is locally available, you can also create a bands in terms of the timber, or you can have a band in terms of the reinforced concrete. Now, as you can able to see, the timber provides you an opportunity to provide the band along the across the height of the wall at sea level, or even below sea level also. But when you have a reinforced concrete band, it does not allow you such kind of the flexibility. So therefore, in old construction, or some of the construction in hilly region like in Jammu and Kashmir, you will find out such kind of the typical feature of using a timber at various level across the height of the building. But this is very effective way of doing a retrofitting, a simple and effective way of doing a retrofitting. The another important way of doing a retrofitting of masonry structure, typically very well suited to a stone masonry building, is a tie application. So you need to tie the walls by the reinforcement, and this reinforcement are being tied throughout the length of that particular wall, and that's how they are holding. They are creating a bad joint, and then they are holding the wall all together and try to create a box type of the structure. And in latest applications, some post tensioning has been done. Of course, I have not personally seen such kind of the application in India, but so this kind of the applications have been in practice in some of the European countries, New Zealand, and maybe in Canada for some of these structures. So here you will find out that they have been using a different kind of the pre-stressing anchor, which is coming outside, and then they are pre-stressing it, and they are applying the load from through the jack, and they are holding the long walls of masonry structures, and some of them are big heritage structures. Here also you can see some of the photograph wherein the people have used this anchor bars along the length of the building as well as across the height of the building, as you can able to see from this picture. But this post tensioning is not very common sight in our own country. Of course, such kind of the short creating application is common in our own country and common to the countries like USA and UK, where a big heritage structure, long-standing walls, they have been first placed with a reinforcement mesh, and then they are using doing a short critting. So this is one of the photograph after California from earthquake in California city. As you are aware, California is sitting on the ring of fire. So after a Long Beach earthquake of California, one of the famous earthquake, they have sought doing a such kind of a short critting applications for a masonry structures, and such kind of the short critting methodology is also very common in New Zealand, and some of them are, of course, some of the pictures here they are taken from USA, but these are some of the short critting applications. After doing a short critting, how the thickness of the wall has increased. But as you can able to see from this picture, that inside it is a masonry wall, and outside there will be a short critting applications that people have done. And this is again typically used in a certain part of the world. It is called overlays. So typically one of the very long walls and effective seismic retrofitting strategies is providing a overlay. So overlays are, they are nothing but a different type of anchors in a different pattern. They are breaking the unsupported length of the wall, and they are typically done by using a reinforcing steel, and they have been using a shear connector. So as you can see, it is a sheet type of the reinforcement they have placed by taking up one of the brick unit or some of the brick unit along the length of the wall, and then they are putting the reinforcement, and then they are also grouting it afterward. And the depth of such kind of the overlays, it varies from the from as low as 75 mm, but goes maximum up to even 250 mm. So as you can able to see, of course, depending upon the thickness of the wall, you can have a different type of the overlay application. Again, this is not very common in our own country, but they are commonly used in other country. However, nowadays there is an increase into a solution in terms of the FRP overlays. So people are using the FRP, CFRP, and GFRP sheets in order to retrofit the masonry. Of course, they have their own issues and challenges because CFRP, GFRP sheet undergoes a brittle failure. So there are certain issues, but people are using it. And some of the other type of the retrofitting strategies that we have tried to work out along with the guidance of Professor K.S. Jagdish of IISc Bangalore, that anyway I will quickly cover, and I will try to finish it as quickly as possible, as I know you have another session. But the last part of that, we have tried to do some work in masonry structure using one of the semi-sophisticated but unique facility available at our own university called shock table. So typically after retrofitting, you can understand the dynamic behavior, or you can find out how much improvement that happened after doing all this retrofitting on a shake table. But as you are very well aware, shake tables are very costly and they are not into the reach of everyone. And therefore, we have a semi-sophisticated shock table facility, which is economical, easy to install and operate, but of course they are not as sophisticated as shake table, and it gives a shock loading, not the continuous earthquake loading, but it can give a very good insight of dynamic behavior. This is the schematic diagram, and this is the picture of the facility what we have. and then we have used some instrumentation. I'm just running over it because of the paucity of time, but you are very well aware, some of you are very well aware, we are using accelerometer, we have a data acquisition system from NI, we have a LabVIEW software and the computer system in order to measure the dynamic behavior in terms of the vibration, in terms of the signals, vibration signals, and then we have been using this. And what we did is we have started with all sort of codal provisions implemented on building models. So we have done it with a concrete blocks with a different kind of the provisions given in IS 4326, and where you can find out there is a right hand side is the model without adhering to the codal provision of 4326, left hand side with the codal provisions of 4326. You have a band at roof level, you have a cable band at the roof level, and then we have given a shocks, and we found out that the model with a codal provisions, adhering to the codal provisions, they sustain a more energy as compared to the other model. Other model, you can see out of plane bending of the long wall, there will be a shear cracking into the wall, but here you can see it is an inch ampere, or they are just at the beginning of the failure as far as such kind of the model with a retrofitting strategies that as per 4326 is followed. And you can find out after certain shocks, the building without the retrofitting measures as per codal provision has completely collapsed, while the other building with a retrofitting strategies as per 4326 or features as per 4326 has survived. And you can see some of the kind of the failure, shear failure that has happened into a building with a earthquake resistant features, but they have still put it into a shape, and it is taking certain load. And then we have tried to look at various bands, the effect of various bands. As I told, we have used certain bands other than what is provided in 4326. So this is as per 4326. This model number on right hand side is as per 432. So it means roof band and the seal band. But we have also provided in other model, other building, other seismic band below this seal level. Below the lintel level, at the intermediate level of opening, below the opening, that is at seal level, and below seal level. And obviously you will be able to see that the building with a more number of lintel band has reduced the effective length of the vertical wall, and therefore it has survived better as compared to other model. And then you can see it has not completely collapsed. This other model has completely shown a disintegration from the corner, but not the one with the band. And you can see after certain shock, the one which has given following IS 4326 has collapsed, but the one which is improved capacity with this seal level band and other than seal level band, that has improved its capacity. And then we have brought it our own hand because we wanted to see how it has been brought down, but it has not been brought down because of the testing, but it has been brought down because of our intervention. Similarly, some other models have also been tested, which I am just moving across, but here we have tried containment reinforcement. So one of the model is as per IS 436, and other model we have used this containment reinforcement using aluminum wire or GI wire. So these are the typically GI wire which has been put across in vertical direction to avoid the out of plane bending of the model, and we have seen that it has been worked very well. And after that we have also tried to model and test with our some postgraduate student. We have tried to test it the freestanding wall with a different features like horizontal vertical horizontal reinforcement, vertical GI reinforcement, both horizontal and vertical GI reinforcement, and obviously the last model has worked very well. And then later on we have also tried to do it with a PP band, and such kind of the PP band based experiment was also been done with a stone masonry, which has really worked very well. These are some of the output. But the containment reinforcement is an outcome of Professor K.S. Jagdish, who have given an idea that once you put the wall outer side containment reinforcement, then it improves the bending capacity, because you know any wall under bending, if there is no reinforcement, it cracks from tension side. If you put a reinforced concrete element, you know the cover concrete will get start cracking because of tensile stress. But when you have a masonry wall connected with a containment wall, the containment reinforcement, it will really help to take care of the bending very well. And these are the different way to put a containment reinforcement. This is not a confined masonry. This is a use of containment reinforcement. So do not get mixed up with the confined masonry with the containment reinforcement. And then various such kind of the strategy was done after Nepal earthquake in our own backyard. So we have tested various stone-based masonry structure with a vertical containment reinforcement, 1 story, 1.5 story, and 2.5 story. And we have done a testing on the shock table facility, and we have seen that this containment reinforcement really works very well. And recent past, we have done a very innovative experimental study where we have replaced a masonry structure made from red clay brick to a AEC block in order to reduce the overall weight and in order to reduce the hazard. So we have done a all laboratory testing in our lab. With this left hand side shows the mechanical properties obtained experimentally. These are the mortar strength obtained experimentally, and these are the different stretcher bond and English bond that is developed for an AEC block. And then we have developed a two model, one with a stretcher bond and another one with the English bond. And then we have subjected to the shock loading, and this is the instrumentation of that particular test. And then these are the different records. Of course, I am running little bit faster here. It is very interesting, but these are the different experimental output in terms of acceleration that we have obtained for a varied degree of the shock. And what we found out, and we have mapped the damage also on a piece of paper. So we have prepared the on the piece of paper the model, all the four sides of the wall, and we have tried to map the damage as soon as you go along with the socks. Of course, you can find out more detail in the paper available now and published now. And these are the real pictures that you can able to see of the damage that has been performed at our shock table. But most important outcome is that obviously the AAC block reduced the time by a half as compared to red clay brick, but most importantly, stretcher bond relatively perform better as compared to English bond. And the major failure is out of plane bending because of the flexure of the long wall. But the AEC block building model is behaving at par with the red clay brick based building model, which we have all tested earlier. And obviously, it will reduce the seismic hazard because of the reduction in weight as well as the acceleration. And obviously, some of the challenges that we nowadays face for a masonry structure is the cost of masonry unit because of the decreased manufacturing unit. We have a rapidly decreasing construction of masonry structure, except some iconic structure, or we want to prevent or preserve the history, or we want to make live, retain our history, historical monuments. Only that purpose we might develop or we restore, or an effort by an individual. Otherwise, we have a very negligence towards the masonry structure. Of course, as far as retrofitting is concerned, we have a lack of expertise at local and national level in terms of the design and application. And the cost of retrofitting is also higher because most of the retrofitting material that we procure from outside, or it has been imported, and therefore they are not they become expensive and not cost effective. And obviously the lack of awareness, mostly we are being procrastinated with the view of the RC structure. We don't want to construct the masonry structure, and we don't want to still live in a masonry structure. And obviously the lack of policies and the support from the government. And what will be the way forward? Obviously, we need to have some development of the skill set. We have to have some research effort to be done from research organization, academic institutions, and other stakeholders that require to be increased. We have to have some policies and support from the government toward retrofitting. And obviously, we have to look as an engineer, look at some cost-effective and locally available material as a retrofitting measures. So some work that we have also tried in our own laboratory here towards this one, and one of them is this vertical containment reinforcement, which really works very well. So these are some of the views from my side, and I'm really acknowledging the effort apart from other sources. I deeply acknowledge the efforts and the gratitude to our Professor K.S. Jagdish, Professor Svetlana Brazev, and Rajendra Bhai and Rupal Ben, with whom we have conducted some of the shop table based studies, and we have a lot of interactions and association over a period of the time. So with that, thank you very much. I'm sorry for overshooting the time, but thank you very much for your kind support and listening me. So thank you very much, sir.
Thank you, Purohit sir. Thank you.
So if you have any questions or anything, you can definitely pass on. If any participant would like to ask, I would try to answer in best of my abilities. Else, they can write me an email also. No issues with that. But I think I just leave it to you depending upon the availability of the time. Otherwise, I'm absolutely okay if someone have any questions.
Please raise your hand if you have any query regarding this session.
Yes, good afternoon, sir. Can I say, am I audible, Purohit sir?
Yes, ma'am, you are audible.
Yeah. First of all, sir, thank you really very much because indeed I feel that overall the complete nuances which you have covered for the seismic retrofitting of masonry structures, it was truly great. And of course, to see that so much work has been done, particularly at Nirma University. So that is incredible. Sir, I just have a question. Of course, my very first question was probably answered in the last second slide of your presentation, wherein you mentioned about the challenges. What question I had in mind is, sir, that whenever you talk about masonry, nowadays the moment you talk about red brick, fly ash brick, or any such form of a masonry unit, everyone says that now it's going to be obsolete. Like, you're not going to use it anymore. As such, if you talk about G plus 10 or I mean in the high rise structures, or not,
Correct.
let's not high rise structures, but all the real estate schemes which are coming up. So they say that they are just as a part of infill wall. So, sir, shall
Right.
we say that all these studies like earthquake performance or seismic retrofitting is now going to be limited to a very rural setup, or let's say in such as Nepal or somewhere Assam, or where still the new technology is yet to come up.
Correct. Yeah, ma'am, you have raised a very important concern, and as a community, I think most of the time, as I said earlier, also that we are somehow little bit giving a less importance to this masonry structure. So, of course, it becomes limited to only rural area because there they do not afford to go and switch over from masonry structures to the reinforced concrete structure. But in recent some of the deliberations that what we had, in fact, I had one of the feedbacks available from USA at least 3 4 years back, that people are now thinking stop constructing the reinforced concrete structures because they become more hazardous and leading to more devastations under an earthquake. So people are trying to go back to some of the old technologies. In fact, the timber structure is also coming up in some of the developed countries again. Some of the masonry construction is also coming back in a big way. But as you rightly said, that this becomes this technology or innovation becomes done at very small scale level. There are only few individuals involved worldwide. There are few universities, few researchers who are doing the work in masonry, and because of that, there is a limitations of this innovative technologies coming up. But as you can say, as you can able to see that in after 2015 earthquake, along with the Professor Jagdish and the Rajendra Bhai and Rupal Ben, we have tested this GI based containment reinforcement, and Nepal government has adopted it, and they have been now constructing all such kind of the masonry structure into the Nepal because people do not have any other choice. Given and said the situation, if the people have a choice, they do not want to restore the structure, which is another part of the story. But that's how we are facing a lot of challenges. But still, we have a huge amount of the masonry structure existing in our own country, and there is a potential to come up with a good retrofitting strategies and good retrofitting application services so that we can make those structures safeguard. But this becomes true to a certain extent that only people living into Assam, Jammu and Kashmir, some of the Nepal or some of the countries where they do not easily switch over to a reinforced concrete structure, or there will be an issue related to transportation of reinforced concrete
Yes.
elements like cement and others. They are still going ahead with this masonry structure, but for them this becomes very very important and very very crucial part for their livelihood. So I think that is what I can say. I hope I have tried to answer
Yes.
your queries.
Yes, sir. I mean, the last work which you showed, which you carried out with your student Sharad. So, what prompted you to work on AAC blocks? Because, sir, as far as I mean, I see the AAC blocks as something which is still seen in an urban aspect. If you see, it
Right,
has still not penetrated the rural area, because in rural areas, sir, what my observation is, whatever local stones are available over there, they
correct,
generally tend to construct their three-storied or two-storied houses out of that, and they
correct.
are quite bulky, quite heavy. And I mean, forget about, sir, all this bond and compressive strength which we are talking, because that has no connection, like, even from far ends. So, sir, what
True.
basically prompted you to get into this performance of AAC blocks?
Correct. So obviously the first of the thought that we prompted when we start working on it was that at least to reduce the seismic weight of the structure, typically masonry structure. And second one is the falling hazard. So recently you might have come across that there are certain good iconic masonry structures are coming up in a big way. And one of them is, perhaps you might have heard about Nalanda University. So
Yes.
Nalanda University has completely a exposed brickwork, and some of the structures are load-bearing structures with a red clay brick. So we somehow we were involved into that also. We were blessed to be associated with it. But at that time, whatever the brick that they have developed, of course, indigenously developed, but they were also very bulky. And the one of the concern was their falling hazard of this the red clay brick or innovative brick, which I am not revealing the name because it is pertaining to some other agency. So I should, with the ethics and moral basis, I am not repeating
Yeah.
and revealing the name. But they were very much concerned about falling hazard. That has prompted us that even a red clay brick will fall from certain height of around say 10 feet or 11 feet or even 6 or 7 feet. They lead to a huge hazard to a human being. And therefore we think of that, can we reduce the seismic weight of it, can we reduce this falling hazard by utilizing a low density element. And low density element which is now available at present to us is a AEC block. So therefore, to trigger out or to understand whether it is really performing at par with the red clay brick masonry or not, whether we can really work out with, or we prepare the model using masonry structure or not. But with that initiation we have started, and by God grace we could able to get a very good outcome of this and very good composition of the masonry structure. Of course, this is very very infant stage, but that is how it has prompted us to work in this direction. I hope
Correct.
I'm
Yeah,
clear
yes, sir.
to.
Sir, absolutely. You have indeed answered it well. But sir, actually, when you talk about all this, it really gets bit the mind. It gets into a debate side, because
Yeah,
like it is we really don't see AAC blocks penetrating our rural areas still.
correct,
I mean, at least
correct.
in coming 10 years, maybe.
Correct, correct. But
Yes.
I think that is how perhaps we as an engineer and perhaps as a community we need to think, because it is really very, very low in weight. We have used this AAC block which is around 750 kg per meter cube. To be very
Correct.
precise, 769 kg per meter cube. But if we can, and of course some of them are now people are working with a fly ash based concrete block. So they are replacing the same cement also with this fly ash. So if we can really work out some of the strategies where we can use this waste material and we
Yeah.
try to get it penetrated up to a rural area, I think that would be a really good initiative. But obviously, we have to
Yes.
work very hard.
Sir, I'm just why I'm saying this, because sir, it got a bit ambiguous over here, because just yesterday we had this lecture from Dr. Durgesh Rai, where we were
Right,
talking about confined machinery. Now
Right.
there, sir, it so happened that he just cited that he won't prefer AAC blocks to be much in use as far as the confined machinery is concerned, because again the compressive strength goes below 7 megapascal.
Correct.
So sir, actually, I do not know how we are going to fit in all these units to actually cater to the requirements.
Yeah.
So when we go for confined machinery, is that the brick unit strength at least should be more than 7 megapascal.
Correct.
So wherein the AAC
True.
blocks doesn't fit in.
Yeah, you're true. But I think we are looking towards a certain category where we are not aiming with a very high-rise kind of a masonry structure. Maybe a small unit, either a ground story or maybe ground and a half story with a much reduced seismic weight. But of course, we have not done any testing in terms of the confined masonry. And obviously, I think what Professor Durgesh Rai sir has said is absolutely right. The strength what we achieved in our AEC blocks is, you might have seen, around 5 Newton per mm square. So obviously it is not a good candidate for confined masonry, but for a very small scale unit, low scale unit, maybe a rural area, perhaps we can think upon. Of course, we have to work really much ahead into this in order to make our point navigable in terms of policies and other things. But we have just attempted this out of our own curiosity and research efforts.
Absolutely. Sir, actually nothing against the work you have carried. I'll tell you, sir, because being a researcher myself, I'm speaking to you in this context because I myself am working in where I'm coming up with an alternative construction unit.
Right,
Now, the thing is that I am getting a very good strength. Of course, it's an unburnt material. It is using the waste. So that's
right,
what I was bothered, but somehow I'm going on a higher side on a weight point of view.
right,
So, so that a unit which is coming out to be in a weight of 3.5 kgs with a
right.
28-day compressive strength of 18 megapascal.
Okay.
Now, I speak to so many people in the industry. They say that ये है ना weight का problem हम create करते हैं. मजदूरों को weight से कोई issue नहीं होता है. In fact, there
True,
are I mean, so there are so many structures like resorts or this they actually look for heavyweight units also.
true,
So actually, sir, I really do not think so. One should believe that positively. One should work in and research in this area, so that maybe because an alternative unit is also the need of the hour.
true, true.
Correct.
Yeah,
Right.
yeah, absolutely true. I
Okay. Okay.
think, yeah, but the cohesive effort from all of us can definitely pave a way forward, and we can do something better for society as a whole. So I think it is collective effort that we need to do. So we need to integrate that research that has been happening in bits and pieces at different parts. So once again, I congratulate you for doing some good work, and hopefully such kind of the thing will get integrated down the
Yeah.
line.
Thank you. Thank you very much, sir, for answering it all patiently. Thank you very much.
Yeah, yeah. Thanks for the discussion.
Is there anyone has query regarding this session? Please raise your hand. Okay, I guess no one has query. Sir, thank you very much for answering all the questions. And it was a really interesting and useful, informative session for all of us. Sir, it would be great if you can share your PPT with us.
Sure, definitely, definitely. I will do it now only. Once I will go out of this session, I will immediately share the PPT. So I have no problem. I will send it to Professor Sangvi sir. Okay.
Okay, thank you very much, sir. Now we will have a break till 2:30. Next session will, yes, sir.
Pure Sahib, thank you very much.
Yeah, thank you, sir.
Yeah, it was a really very good lecture, and I think you have covered most of the features of masonry structures, and I think what you have done at Nirma University is also very good. So we appreciate that. Thank you very much for sharing your experience and your
Yeah,
expertise.
thanks a lot, sir. I think the pleasure of all minds that you have allowed me to share with some of the work and some of the experiences with the participant. I hope that there are so many young engineers will take it forward, and the huge thanks goes to you and your team for allowing me to share these things. So thank you once again, sir, for your.
Yeah, sir, thank you very much for accepting the invitation and delivered a wonderful lecture. Thank you.
Thanks a lot, sir.
Yeah.
Thanks. I will share the PPT immediately. Okay.
Yes. Thank you.
Thanks. I once again wish all participants a happy learning and wish all the success to the short-term training program. I'm sorry, I mean FDP, and I'm sure there is huge learning through this FDP. So once again, thank you. Thanks, and do take care, everyone. Take care.
Okay.
Bye.
Bye.
All the participants and students just remain in the meet. We have to take a screenshot of the group. So all of you are requested to turn on your videos.
All the participants are requested to switch on the camera. We want to take a photo. So please switch on your camera, please.
All the participants are requested to on their camera.
Are we audible?
All the participants are requested to switch on their camera so that we can take a screenshot quickly.
And we also want the smiling faces.
Yes.
You have to remove all the distress and remember the yoga sessions, what we want in the morning. We have to be so fresh, right? Yeah.
Yes, sir. It's absolutely correct, sir.
Yeah.
Just a minute. Okay, thank you very much.
Thank you.
Yes, so now we will have a break till 2:30. Next session will be conducted by Dr. Kaustav Chatterjee, sir, on design of pile foundation under earthquake forces and soil liquefaction at 2:30. Now you all can leave this meeting and join at 2:30. Thank you very much.
Thank you, Amira. Thank you.